Welcome back. Today we are going to continue with the structure of networks, and there is a lot to be understood in terms of the importance of a given node in network structure. So, if you look at graph theory and network science, one of the key applications, in fact all of the key applications involve identifying a bunch of important nodes, a bunch of important edges or groups of nodes and edges and so on, which we will talk about shortly. So, today let us focus on identifying important nodes in the network. So, how do you deem that certain nodes are important? In fact, the picture that you see on your screen is a yeast protein interaction network, and the nodes are colored based on what happens to yeast when this protein, the protein corresponding to your node on the screen, is deleted from yeast. This was done experimentally, a fantastic experiment more than 20 years ago. So, any red node means that when deleted, the yeast did not survive. Yellow nodes, they could not perform the experiment or whatever. Orange nodes are when the yeast was a slow grower following deletion, and green nodes are when nothing happened to the yeast or the yeast survived following the deletion. Can you actually identify which nodes are important just based on looking at the network, right? So, they did this experiment, a painstaking experiment, expensive experiment, but fantastic experiment. But can you actually predict by virtue of a node's importance whether it is going to be essential in the yeast's protein interaction network or not? We will try to address these kinds of questions by looking at centrality measures. The first and the simplest centrality measure that we have is known as degree centrality. So, what is degree centrality? This also stems from the fact that nodes with a higher degree are meant to be more important. We already know what degree is. What is degree? Degree is the number of edges that emanate from a given node or number of edges incident on a given node. In an undirected graph, it does not make a difference. So, for A, there are 4 edges, so the degree is 4. For B, there are 3 edges, so the degree is 3. For C, there are 3 edges again, so the degree is 3. For D, there are 3 edges again, so the degree is 3, and for E, there is only a single edge, so its degree is 1. So, these are the degrees for each of the nodes in this very simple graph. What you can also have is, you can normalize this by total degree or something like that. So, here the total degree is I think 14. So, you can have degree centralities as a normalized version, where you have degree centrality of A is 4 by 14 and E is 1 by 14 and so on. So, there are various ways to compute the importance of a node, and just based on simple degree is one of them. Okay. So, the next interesting method is called closeness centrality. Closeness centrality seeks to quantify the centrality of a node based on its proximity to other nodes in the network. So, first there is a measure Li that is calculated, which is sort of like farness. So, how far is a given node from all other nodes? Okay. So, for this what you do is, what is the average distance of every other node from a given node? So, you start with a node A, how far is C from A, or how far is E from A, how far is F from A, and so on, in terms of its shortest path. It could be 1 hop away, 2 hops away, 3 hops away, based on shortest paths only, not like roundabout paths and so on. And the average of these is going to be Li, right. So, you look at the formula, it says sigma Dij for all nodes and except to itself, which is anyway going to be 0. So, you do not include it in the numerator and you also do not include it in the denominator. So, you divide by n minus 1. Okay. And this obviously makes sense for a connected graph, right. Otherwise, you will have like an infinity that will obscure things. So, let us now take an example. Let us look at the node G and study its closeness centrality. So, for the node G, the distance from A is 1, from B is 2, from C is 2 again, from D is 1, E is 2 and F is 2 again, right. So, and the denominator is obviously going to be 6, because you have 6 nodes A, B, C, D, E, F, and the Li is going to be 10 by 6 and closeness centrality is therefore going to be 0.6. Into the video. So, for the given network, closeness centrality of nodes A, B, C are A, B, C are 11 by 6, 15 by 6 and 15 by 6 respectively. What are the closeness centralities of D, E and F? Since this is a symmetric node, the answer is quite obvious. It is going to be the same. Now, let us look at another very interesting centrality measure. So, there are multiple centrality measures, and one measure of centrality can be inferred from simply connectivity, right. So, degree is a measure of how important a node is, but there are cases where a node may not be very connected to too many nodes in the network, but might still be very important in the graph. So, as an example, let us now consider a simple graph. When I remove this node from the graph, you can imagine that the graph immediately becomes disconnected. So, even though it has a degree of nearly 2, it is still very important in the context of the network. So, how do we capture such kind of importances? And this is captured through a metric known as betweenness centrality. What does betweenness centrality do? The formula might seem complicated to begin with, but basically what betweenness centrality captures is that how likely is a node to come between two nodes when you travel in the graph. So, how often is a given node between two other nodes on shortest paths in the graph? This is the kind of question, this is the kind of quantity that we are seeking to capture using betweenness centrality. So, how do we compute betweenness centrality? For a given node k in the graph, so CB of k is given as the fraction of shortest paths that pass through k, the number of shortest paths that pass through k divided by the total number of shortest paths. Okay. So, sigma ij is the number of shortest paths between I and j, and sigma ij of k is the number of shortest paths from I to j that actually pass through the given node k. Okay. And you sum this across all possible paths for I and j. Okay, so this is going to be a sum of several fractions. Now, let us look at a simple example. Let us say we want to compute the betweenness of the node B. So, we need to look at all shortest paths in the network and whether or not they pass through B. If they do not pass through B, it is anyway going to contribute nothing towards B's betweenness centrality, but if they do pass through B, it is going to contribute something. So, what we do is we look at all shortest paths in the network, right. So, we have to sum across all the shortest paths in the network and look at we eliminate those that begin or end at B, begin or end at the node of interest. That is what is captured by I not equal to k not equal to j, and we are going to sum up these fractions for every single path in the network. So, you can imagine how many paths we have in this network. We are going to have every pair of nodes, we can look at a path, and of course, we will eliminate those that begin or end at B. So, we are going to look at AE, AF, AG, and we also leave out edges, right. So, because it says we will not have edges. So, we are only looking at paths. And note that we will only be looking at paths, so we will also leave out edges. So, now you have AB, AC, AD are edges. So, AE is the first path to be taken care of here, AF, AG, and then same way BA we do not need to consider, BC is an edge, BD is an edge, again we look at BE, BG is also an edge, BF is also an edge. Similarly, we look at CE, CF and CG, and then we look at DG, DE, DF are all edges. So, we look at DG, EG because that is again a path and not an edge, EF is again out, and ultimately FG. So, these are all the pairs of nodes that we need to consider. So, this is going to be how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right, and that is basically you have 7 nodes here. So, 7 C2 minus the number of edges here. So, how many edges do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Which is 10. So, now what are the number of shortest paths between A and E? Okay, so you have A, D, E, that is the only shortest path, and of course none of those pass through B. Between A and F, you have two shortest paths, you have ABF and ADF, half of them, one of them passes through B, so the contribution to betweenness centrality is going to be half. Okay, and now for A and G, you have only one shortest path, and that does already pass through. Then we ignore BE because it is a source node. So, let us so that is not going to contribute anything, and then you look at CE where you have only one shortest path and none of it passes through B. For CF you have two shortest paths, one of which passes through B. For CG you have only one shortest path which does pass through B. For DG you have again one shortest path which does pass through B. And for EG you have two shortest paths, EDBG and EFBG, and both of them pass through B. And lastly for FG you have only a single shortest path which does pass through. So, now these are the values. So, you have 0 from here, 0 by 1, 1 by 2, half, 1 by 1, 1. This is ignored because this is a terminal node. It is still convenient to reckon it because it tallies with this number, right. You have to otherwise leave out all the pairs basically starting with B. You can ignore these you can ignore these sort of pairs of nodes, right, like B, E from the computation as well. It's up to you, either ways it can be done. And then we look at CE, which is going to be 0 by 1, so it's 0. CF, half the paths pass through, so it is half, and then all the remaining paths are only through B, there is no other way. So, the betweenness centrality is going to be an addition of all these fractions. So, it's sort of a complicated quantity in that you make so many fractions and then you add all of them up to compute the ultimate value of betweenness centrality. So, the total betweenness centrality is going to be 6 because you have half plus 1, 1 and a half, 2, 3, 4, 5, 6. So, you have half, 1 and a half, 2, 3, 4, 5, 6 when you add up all of those, and you get betweenness centrality of B as 6. So, here K is basically nothing but your B here. Okay. So, look at this example network, and it tells you that different nodes hold a different importance in this network by virtue of different centrality measures. So, if you look at the node with the highest degree, that is going to be 1 because it is connected to so many different nodes, right. So, 1 has 1, 2, 3, 4, 5, 6, 7 nodes it is connected to. But if you look at betweenness centrality, node 9 has merely 3 edges, so its degree centrality is low, but if you look at its betweenness centrality, it is really high. And if you look at the node with highest closeness centrality, that is again a different node which has a relatively lower degree, it is like 1 less than 1, but it still has a very central position in the network by virtue of its closeness centrality. So, the point I am trying to make here is that you have different centrality measures, and we are going to look at a few more, and each of these capture a different aspect of a node's importance in a network. So, it is not to say that the node with the highest degree centrality may be the most important one, or the node with the highest betweenness centrality may be the most important one. Typically they are, and it really depends upon the context as well. For example, if you are looking at communication in a network, then nodes with high betweenness centrality become very important, and we will revisit this when we talk about perturbing networks. So, how do you break down a network very easily? What is the fastest way to break down a network? Do you target based on degree? Do you target based on betweenness centrality? Do you target based on closeness centrality, or whatever? So these are questions that people have asked and answered, and we will see that there are very interesting results that we can look at. So now for this network, can you identify the nodes with the highest degree centrality, closeness centrality and betweenness centrality? Now let us look at another very interesting centrality measure. This is called Eigenvector centrality. What is Eigenvector centrality? Think of this as an extension of degree centrality, and very interestingly you also have a connection to page rank. It's essentially one flavor of Eigenvector centrality, if you will. So think of it in this way: instead of a uniform contribution from each of the neighbors, right, that is what degree centrality happens. So if you have a node A and it is connected to 7 neighbors, each of those neighbors contribute uniformly, equally to the node's degree. So you say it is 7 or 7 by 14 or whatever, right. So by total degree 7 by some m. But if you took it in this way, that nodes that already have a higher degree have a higher contribution to its neighbor centrality, right, because they are influential neighbors. So can you think of that? And in fact this is what this is sort of the logic that PageRank uses. For those of you who have heard of PageRank, maybe it is time to digress into PageRank. So PageRank is Google's centrality measure developed by Larry Page, and well, while it is used to rank pages, the name itself arises from the fact that is from Larry Page's name. So PageRank essentially captures what is the stationary probability of visiting a node in a graph and so on, but the basic idea is that the more important a node's neighbors are, right. So for example, if lots of popular web pages point to a particular web page, right, so the probability of reaching that node is going to be higher, because you are likely to find yourself on a popular web page when you are surfing the web, right. And if those high value web pages, so to speak, are making a connection to another web page, so that is going to be an even more valuable connection, or it is going to be a more useful or interesting page and so on. So this kind of concept is what is basically captured by Eigenvector centrality, and you can see how the Eigenvector centrality name comes from. So think of it in this fashion. So you have EI is now some weighted function of Aij into Ej, right. So you basically look at the adjacency matrix, right, you just sum over all the columns of the adjacency matrix and for a given row, and you basically take all those eigenvector all those centrality values, which is basically Ej, and you weight it appropriately. Okay. And this you can see basically mirrors Eigenvector centrality very nicely. I mean your Eigenvector definition, right. So what do you have? Can you see how this is similar to Ax equals lambda x? So can you figure out how this Ax equals lambda x works? Think about it, but here it is. So here x is nothing but your E and your lambda is nothing but your 1 by alpha. So when you take this alpha from this side to this side, you basically get this equation Ax equals lambda x, and in this case the eigenvector centrality for each of the nodes comes out as this for the simple graph. You can here lambda is basically an eigenvalue of this matrix. Okay. So let us just quickly summarize all the network parameters or various indicators of network structure that we have discussed so far. So first is degree, which basically is captured for a single node, but some of these parameters can also be averaged across a network. So which is what I indicate here, right. So when I use this symbol, I am trying to indicate that there are ways to just average it for the entire network. And then you have the notion of then you of course have the notion of degree distribution, which is a network property which tells you what is the histogram of degree going to look like. And then you have density, which is again a network property which captures the overall connectedness of the network in terms of the total number of edges to the number of possible edges that can exist in the network. Clustering coefficient again is a node centric property. It is for a single node in the graph, but you can again average it for a network to see how clustered your network is. Diameter again is a network property. Characteristic path length tells you, diameter tells you the maximum separation between two nodes on the graph, whereas characteristic path length tells you the average separation between two nodes in the graph. And then you have closeness and eigenvector and betweenness centrality, which are basically defined for nodes. And you can also define betweenness centrality for an edge. How do you define betweenness centrality for an edge? You can use the same concept that we discussed before. Instead of looking at this entire thing in terms of a node, what are the fraction of shortest paths that pass through a node, we can translate this to what is the fraction of shortest paths that pass through an edge in the graph. You can just extend the very same definition. And in fact, there is also another interesting property called co-betweenness that has been defined, which takes any arbitrary pair of nodes. They don't need to be connected even, right. So this tells you how nodes even far away from each other on the graph can still have some sort of role to play in terms of the paths passing through them and things like that. And you can easily think about this in a traffic network and so on, right. You may have to pass through a pair of junctions always to get from your home to your destination. So these are things that are very useful to study graphs and get valuable insights about what are the interesting nodes, interesting bottlenecks, interesting edges, interesting roads, whichever way you look at that in graphs. So with this, we come to the end of a bunch of network parameters that we've discussed. I'll see you again and we'll discuss a little bit more about graph structure and network models.